Welcome to Algebra 2, section on graphing functions. This is parent functions and transformations. We will be discussing today what it means for us to have a family of graphs, and what a parent graph is, and then how we know what something looks like just by looking at some characteristics. So a family of graphs are a group of graphs that display one or more similar characteristics. For example, these are different family graphs: constant function, identity function, absolute value function, and the quadratic function. The quadratic function looks like so. Okay, so these are our different parent family of graphs. The parent graph is the graph of the parent functions, and it's the simplest graph. Right here, these are all of our parent graphs. These are some of our simplest graphs. The absolute value function, the parent graph, is f of x is equal to the absolute value of x, which is precisely what this graph is. The identity function, the parent graph, is y equals x. And the quadratic function, the parent graph, is y equals x squared. Notice the constant function is just y equals some number. In this case, it's y equals 2. It's a horizontal line. Notice that this identity function, y equals x, this, we've learned that this moves in slope-intercept form, y equals mx plus b. We'll learn that the b shifted it up or down. The m dictated its slope. So we're going to be seeing that those similar characteristics also happen for absolute value functions and quadratic functions. So we can have a translation. A translation is going to move the figure up, down, left, or right. So for example, we can have f of x is equal to the absolute value of x. We could have a translation be f of x equals the absolute value of x plus 2. This is going to shift the graph. Think about what happened to your function y equals mx plus b and what that plus b stood for. That plus b shifted our graph up or shifted our graph down. Ditto here. This plus 2 will shift our graph from the center. It will shift it up 2. And then from there, we just have to draw our absolute value graph in. Okay? Similarly, we could have f of x is equal to the absolute value of x minus 2. Okay? When we are inside here from the x, that's referring to where we're starting. So instead of starting at 0, 0 for our x, we need to just shift over 2. So here we're starting at 2, and then we would graph that function. Okay, so translation, it's going to move it up, down, left, or right. Reflection, it flips a figure over a line. That's called the line of reflection. For example, our parent graph of a quadratic y equals x squared, we could have it flip it over the negative reflection. So we're going to make it y equals negative x. So here is our parent graph, the quadratic parent graph. Once we put that negative sign in there, it flips it over that x-axis, and now this would be our y equals negative x squared graph. We can view something similar with absolute values. So f of x is equal to the absolute value of x. If we have f of x is equal to the negative absolute value of x, it's going to have the same feature happen. So here would be our absolute value graph. Okay? If we put that negative absolute value of f, it just flips it beneath it. We just reflect it right here to the other side. Okay, so it just flips it. It reflects it. Dilation, it shrinks or enlarges the figure proportionally. This is kind of what the slope is here. Okay, so if I were to take the graph, let's say y equals x, our identity graph, and change it to y equals 4x, this is stretching the graph by 4. So we all know y equals x starts off as that nice identity graph going through the center. If we have y equals 4x, now that's shifting it by 4, so it's stretching it by 4. So instead of going just up 1, we're going to go up 1, 2, 3, 4. And so now our graph has been stretched. And it's that same exact concept for each of these. So, for example, let me just erase this from here and give you another example. if we have our quadratic graph, y equals x squared, so right there, and here we want to have y equals 1/2 x squared. Well, instead of going over 1 and up 1, we're only going up a half, up a half. Over here, instead of being up 4, we're only up 2 on the other side. And then we would be able to graph that in. Okay, so it stretches it. It stretches it or shrinks it proportionally. So we're going to describe the translation in the function and then graph it. So here we have f of x is equal to the absolute value of x plus 2. So this would be a translation, and this we would move 2 up. Notice that's kind of like in the b location and the y-intercept location. So that tells us we move 2 up. So we start at 0, 0, we move 2 up, and then we just plot our absolute value graph. The alternative to this, if you don't catch on quickly to it, is that you can always make an XY chart. But I assure you, getting to know these translations and how the graphs move will help you immensely when we do graphing. Okay, describe the reflection in the function, and then graph it. So here the function is f of x is equal to a negative x squared. So this is going to reflect it across the x-axis. Okay, so if we think about what our original quadratic graph looks like, the original quadratic looks like this. So if we are reflecting it across our x-axis, we just need to take it and reflect it directly down. So there would be our reflected across the x-axis graph. Okay. Describe the dilation. So here we have the function y equals 4x. We see that the slope is, so this stretches the slope to 4. Okay, so here, instead of just going over 1, up 1, we go over 1, up 4, or up 4 over 1, however you want to view it. And there would be our graph of the function. So the very last piece of this is we need to be able to write an equation for the graph function. So here's our graph function. So step 1 is we see that this is an absolute value. So we need to work off of our absolute value function, which is f of x equals the absolute value of x. So we're working off of this, and now we have to go, okay, where did it move? It's normally centered at 0, 0, and it moved 1, 2, 3 down. So it moved down 3, so that means we have a minus 3 at the end. It did not move over in any direction, and its slope is still 1 over 1. So we just say absolute f of x is equal to the absolute value of x minus 3.